Welcome to the Explainer. We're about to explore one of the most monumental quests in all of science, the decades-long effort to build a star on Earth and achieve thermonuclear ignition.
And no, this isn't science fiction. It's a very real problem that physicists have been wrestling with for decades. The answer, it turns out, requires confronting some truly mind-boggling number. To start a thermonuclear reaction, to get fusion going, you have to deliver a power flux of 100 quadrillion watts per square centimeter. Think about that. You're focusing an unimaginable amount of power onto an area the size of a pinhead, and you're doing it in less than a billionth of a second. So, how on earth is that even possible?
Okay, to really get a handle on the scale of this challenge, we need some kind of comparison. A powerful chemical explosion, for all its force, generates an energy flux that falls short by, well, several orders of magnitude. It's like a firecracker next to the sun. A fission bomb, however, that exceeds the threshold. It creates temperatures and radiation intense enough to do the job. And this is exactly why the first hydrogen bombs used a smaller fission bomb as the trigger. But for clean energy, we need a smarter approach than just setting off a bomb. And this brings us to the core concept of inertial confinement. It's called inertial confinement fusion, or ICF for short. The idea is, in principle, brilliantly simple. You take a tiny pellet of fusion fuel and you crush it with such immense and rapid force that the fuel literally can't get out of its own way. Its own inertia holds it together just long enough for the atoms to fuse and release this huge burst of energy. The process unfolds in 3 really precise steps. First, you compress a tiny fuel pellet to incredible densities. Then, an intense energy source, what scientists call a driver, heats it to millions of degrees. And if you get it all perfect, you achieve ignition, releasing far more energy than you ever put in. Now here's the secret sauce that makes this whole quest even plausible. It's a fundamental relationship. The more you compress the fuel, the less total energy you actually need to get it to ignite. The physics here is just staggering. The ignition energy you need is inversely proportional to the density squared. That means if you can compress the fuel to just 100 times its normal solid density, you reduce the required energy by a factor of 10,000. Push that to 1,000 times density, and the energy needed drops by a factor of 1,000,000. This right here is the master key that could unlock fusion. So, how was this actually achieved for the first time? Well, for better or for worse, it's the only way we've managed to get large-scale fusion so far. It's called the Teller-Ulam configuration. It's an incredibly clever design that uses the intense flash of X-rays from a primary fission bomb, and it channels them inside a special casing called a hohlraum, basically a radiation oven. This creates a perfectly uniform, crushing pressure that implodes and ignites a separate capsule of fusion fuel. This technique is the very foundation of modern thermonuclear weapons. But let's be honest, using a fission bomb as a trigger is a messy, inefficient, and pretty dangerous way to start a fusion reaction. As this quote gets at, the early hope for small, clean, fission-free fusion bombs, well, that's kind of faded. And that has pushed scientists on a decades-long quest to find something more elegant and a lot more controllable. And this brings us to the grand scientific race, the hunt for a powerful, controllable, non-fission trigger for fusion. This quest has really split into 2 main paths. The first is direct drive, where you just hit the fuel pellet directly from all sides with your energy beams. The second is indirect drive, which mimics that Teller-Ulam design, but on a tiny scale. You fire the beams into a hohlraum, creating that perfect, uniform bath of X-rays that then implodes the pellet inside. So what are these high-tech spark plugs? Well, within both direct and indirect drive, scientists are exploring a really fascinating range of drivers. Let's take a look at the top contenders. First up, we've got lasers. And we're talking about massive systems here. Some are the size of a football stadium, designed to focus hundreds of powerful laser beams onto the target. This intense energy instantly vaporizes the outer layer of the fuel pellet, blasting it outwards and creating this inward-crushing rocket effect that implodes the fuel. Next, there are particle beams.
So instead of light, these machines use powerful accelerators to fire intense beams of ions at the target. The big advantage is that because they have mass, these ions can deposit their momentum and energy more directly and efficiently into the fuel than photons can.
Then there's the beautifully direct approach of impact fusion. It is exactly what it sounds like, a hammer and anvil, but on a microscopic scale. The goal here is to accelerate a tiny projectile to hypersonic speeds, hundreds of kilometers per second, and just smash it into the fusion fuel. And finally, there's the incredible power of the Z-pinch. This method unleashes a massive jolt of electricity. We're talking millions of amperes through a cage-like array of superfine wires. The current itself creates this mind-bogglingly powerful magnetic field that violently crushes, or pinches, the wires inward, creating a superheated plasma and a flash of X-rays that's perfect for an indirect drive implosion.
So why? Why are we on this monumental, multi-generational quest? It's because the payoff would be nothing short of world-changing. The goals are really twofold. First, there's the obvious one, the dream of achieving near-limitless clean energy, right? No carbon emissions, no long-lived radioactive waste like you get from fission. But the second goal, well, it's even grander. Ever since the dawn of the atomic age, pioneers like Wernher von Braun understood that this incredible power was the key to leaving our solar system. A thermonuclear microexplosion rocket, propelled by a rapid series of tiny fusion explosions, is the only known physics that could accelerate a spacecraft to 1/10 of the speed of light. That makes interstellar travel a real possibility, and this quest just keeps pushing into ever more audacious territory. Future concepts like the Super Marks generator propose kilometer-scale machines that could create artificial lightning, gigavolt, high-current beams powerful enough to ignite even harder to burn but ultimately cleaner fusion fuels like pure deuterium. This ongoing quest to capture the power of a star isn't just some technological challenge. It's a reminder that the fundamental laws of physics are themselves a frontier. Mastering this power won't just change our world. It's going to challenge our very imagination to decide what we do next.